Okay, so we mentioned that this is the equation, but what's, in my opinion, is more important is that, there's a reason this is called negative binomial, right? And the reason is that you basically say that the last guy must be a success. So the last experiment must be a success. Before the last experiment, it's a binomial distribution, right? And this is, in fact, the proof for this distribution. The proof is quite easy. So let's look at one example, right? So the probability that a camera passes a test is 0.8, and we know that the cameras are independent. What's the probability that the third failure is obtained in the fifth test, right? So here, for example, we are interested in having 3 cameras that fail. We want to investigate them to find out why they have failed, right? So this means that we want the third failure to happen in the fifth test, right? So this is a failure. This is the fifth test, right? And here we have one of the failures, right? So we have already, used one of the failures that we had. So we have 2 failures here, right? And since the events are independent, in fact, I'm not going to use the equation for negative binomial to solve it, right? So the equation is here, but I'm just going to use binomial, right? So I'm going to say this experiment is a combination of 2 experiments. The first experiment multiplied by the second experiment, right? So the first experiment, I want to have 2 failures in, so I use the fifth experiment here. So in 5 minus 1 experiment, which is 4 trials, right? So I want to have 2 failures in 4 trials. That's the binomial distribution, right? So it's going to be 4, choose 2, times P. So here we have to be careful what we define as success, right? So the question says passing a test is 0.8, and it wants failure, right? So probability of success is 1 minus 0.8, right? So P is going to be 0.2, right? So 0.2 to the power 2 times 0.8 to the power 4 minus 2, which is again 2, right? So this is the binomial part. Now I have to multiply by the last experiment, which I want to be a failure, right? So the last experiment is, the probability of failure in the last experiment is 0.2. So at the end, it's going to be 4, choose 2, times 0.2 to the power 3, times 0.8 to the power 2, right? So here, I didn't use the equation of negative binomial. All I used was binomial, right? And we see that if we use negative binomial, we get the same thing, right? So if here we plug in x is 3, p is 0.2, and r is 5 experiments, right? So if we plug in these in this equation, we get the same answer as here. So in my opinion, negative binomial is not a real, independent distribution. It's like a derivative of binomial. And you can also tell it from its name. Yeah?
Shouldn't r and x, shouldn't the values be flipped? Shouldn't it be x is 5 and y is 3?
So, yeah, I think you're right. Yeah.
Okay.
Yeah, that's a very good point. Yes, you are right. Thank you. Yeah, I should pass you a chocolate. What was your name again?
My name is Mikey.
Mikey?
Yep.
Yeah, that's a very good point. So I did make a mistake, right? So in the negative binomial here, what I wrote here actually is completely incorrect, because now if you plug in here, I'm going to get 2 choose 4, right? Which is 0. there's no ways I can choose 4 from 2 objects, right? The top guy has to be always higher, right? So basically, my mistake was that this is R and this is X. And basically, my mistake was that since I did the binomial first, in the binomial, the number of successes is X. And I thought the same thing here, but they actually flip. I'm very happy that I made that mistake, because the other difference between binomial and negative binomial is that in binomial, X was number of success in binomial, but in negative binomial, X is number of trials. In negative so that's the distinction, right? That's why I made that mistake. Any other questions? Okay. I'm very happy that I do make mistakes, because it shows that you guys are following. Thank you. Okay, so the next, in the next question, the setup is quite similar to the previous one. It's just the wording is a little bit different, right? Here, I'm doing 5 tests, and I want to find out what's the probability of 3 failures, right? So here, the 3 failures can happen anywhere. For example, I can have 3 failures and then 2 successes, right? Or I can have like 1 failure here, 1 failure here, and 2 successes in the middle, right? For the case of negative binomial, only this one counts, right? Because what we are interested in should always happen in the last trial. But for binomial, basically the outcome that interests us can happen anywhere. For example, it can happen in the first 3 trials, right? So because of this, we have to use the binomial distribution here. And so based on the basically analysis that we just did, comparing negative binomial and binomial, which one of these 2 is bigger? Is this one bigger? So the answer, there's no answer here. So the answer is going to be, let me write the answer. So it's going to be 3, choose 5 times 0.2 to the power 3 times 0.8 to the power 2, right? So if you know the answer, raise your hand. Which one is bigger? This answer that we found here, this probability, or the previous probability? Basically, this guy. So first of all, you can find out which one is bigger just by looking at the numbers, right? Or you can find out which one is bigger by thinking intuitively about the meanings. Yeah, go ahead. Scroll down. Yeah. Yeah, dodgy.
Yeah.
Yeah.
I don't understand the difference between /2 and /1.
Okay, yeah, that's a good question. So basically here in flash 1, right, what we are doing is that for whatever reason, we want to find 3 cameras that failed the flash test, right? So the way we do this experiment is we keep testing cameras until we find the 3 that failed the test. And once we find the 3 that failed the test, we stop the experiment, right? So this is the setup in this question, right? And the setup is quite similar to the setup for geometric experiment. Remember, for geometric, what we had was, we said, how many times should I do this experiment until I find 1 success, right? So for example, how many times should I roll the die until I get 6, right? So in that experiment also, what I do is I keep rolling the die until I get a 6, and once I get a 6, I stop, right? So that's basically that's the question here. The question is different. The question is, I'm doing 5 tests. I want to find out what's the probability of finding 3 failures among the 5 tests, right? So here, what could have happened is that I could have, found 3 cameras that fail at the beginning and 2 cameras that pass after that, right? But in the previous case, all of the failures must happen in the last trial, meaning that, in the previous trials, I didn't find, what I was interested in. And that's why I repeated the experiment 1 more time, right? So that's the difference.
Thank you.
So any suggestions? Which one is bigger? Binomial or negative binomial? Oliver? Yeah, go ahead.
The second one?
Which one?
The first one, you're limiting it to it being on the final, having to be the final test.
Yeah.
The other one, you.
Exactly, yeah. So here basically in example 1, you restricted the basically last experiment to be a failure. You said, the last guy must be a failure, right? So whenever you apply more restrictions, probabilities are lower, right? So this probability is lower than the second one. And you can also look at the numbers, right? Both of them have this, so this is the common part. This is exactly the same in both of them, right? Here we have 4 choose 2, and here we have, and here we have 5 choose 3, right? And 5 choose 3 is bigger than 4 choose 2. Right? Yeah.
Is the binomial always bigger than the result of it than the negative binomial?
Yeah, if the numbers, that's a good question. If the numbers are the same, for example, like we want 3 failures in 5 trials, or we want, like X failures in Y trials, then yes, always negative binomial is smaller than binomial. Yeah, because always in negative binomial, we restrict, right? We make a restriction that the last experiment must be, what we define as success. And that's another, thing that might confuse you, because in this question, we define failure as success, right? So remember, in these experiments, we define something as success, right? So here, failing a camera is defined as success, right? Yeah?
Can you repeat again why in the first, not this one, we use negative probability?
Yeah, so basically, let me use a blank space. So here, for both geometric and negative binomial, the number of trials is a random variable, right? So for both of these, the number of trials is, so it's very, very common to denote random variable as RV, right? It's not recreational vehicle, right? So whenever I wrote in this class, whenever I write RV, I mean the random variable, right? So here the number of trials is a random variable, and that means that I stop doing the experiment until I find, for the case of geometric, 1 success, for the case of negative binomial, X successes, right? So so in these cases, we have to use either negative binomial or geometric distributions. Did I answer your question? Yeah. So I know that these sound quite similar. The only way you can really understand them is to do many sample questions. And I suggested this to you before. I basically mention it again because it's quite important. When you solve the suggested problems, don't look at the solution, right? Like always do your best until you make sure 100% that your answer is correct, and then look at the answer. Because always if you look at the answer, it makes sense. Yeah?
So just a quick question. The suggested problems, to where it's covered? It's covered.
What do you mean?
I mean,
It
like,
covered the entire book.
The entire book?
Yeah.
Oh, you mean the ones, of course, outline?
Yeah.
No, I mean the ones that you have written and solved them.
Okay.
They're all suggested problems?
I don't understand the question. What is the question?
Okay, the problems that you have just like posted them on Moodle with a PDF, and you solved them.
Yeah.
These are the ones in the course outline?
Yeah, those are the same ones, yeah.
All of them?
Yeah, those are the same ones, yeah. Yeah, so the reason that I posted questions, I was hesitant to do that because those are copyright material, right? It's from the book, and the book is copyright material. But I realize many of you have the new version of the book, and the numbers do not correspond, so I actually posted the questions so that you actually see the questions. Yeah, but it's the same thing.
Okay, good.
Yeah. Okay. So the final distribution before, there's one more after this, but that one is really simple, right? The final one that we cover in this chapter is hypergeometric distribution, right? And here we basically, you can always think of it as sort of having an urn, right? Having a basket which has k objects that are classified as success and n minus k subjects that are classified as failure, right? And we select n objects from this ball. And another important, basically, keyword here is that there is no replacement, right? Meaning that we don't do the selection by, for example, first selecting one, let's say this is a bowl with a bunch of marbles, right? We don't select one marble, look at it, and then put it back and select another one and put it back and so forth. This is without replacement, meaning that we pick one, we pick another one, we pick another one, and all of them are, so no marble can be selected multiple times, basically. So this is the probability, right? The probability of having basically, actually, I don't say what is the, yeah, so it actually, X is the number of successes. So among this n, we want x of them to be from class S, and n minus x of them from class S prime, right? And the probability of that is basically this equation. Now, does anybody know what is the proof for this equation? It's not difficult, the proof. So I help you a little bit for proof. You don't need anything from chapter 3. You need something from chapter 2, right? So you don't need anything from probability. Actually, you need something very easy from probability, but all you need is counting technique, right? How to count. Any ideas? So I help a little bit more. Basically, we have to use this equation. Probability of an event is equal to number of ways events can happen divided by total number of ways. Right? For example, like if we wanted to see what's the probability of like when we roll a die, getting an odd number, we say there are 3 odd numbers and there's a total of 6 numbers, so it's 3 divided by 6. Yeah, go ahead.
Here, try to get the possible successes times the possible failures divided by the possible ways of doing it.
Exactly, yes, that's correct. What's your name?
Roger.
Say it again.
Roger.
Roger? Yeah, that's correct. So basically, here we have to count how many ways we can have X successes and N minus X failures, right? And we did have an experiment like this before, right? Like we had a ball and like we had a bunch of marbles inside. We wanted to find out how many ways we can pick, 5 blue and 6 red marbles, for example, right? So basically what I want to do is to select X marbles from these K marbles, right? And that's K choose X. That's a combination of X from K, right? And then the remaining N minus X should come from basically the remaining N minus K marbles, right? And to select N objects, I have to select, both successes and failures, right? I have to do these 2. Because of that, I multiply, because it's AND, right? And here, basically, we write down total number of ways that I can select N objects from N objects, right? And that's combinations of N out of capital N. Right? So this is a relatively easy distribution, right? We don't really need the equation. Right? So let's look at an example. It will make more sense. So a batch of parts contains 100 parts from supplier A. So 100 from supplier A and 200 from supplier B, right? 4 parts are selected randomly without replacement. What's the probability that all 4 of them are from supplier A, right? So first, let's not use the equation at all. So basically, I'm going to say probability is equal to total number of ways is going to be in the denominator, and that's the easy part. So the total number of ways I can select 4 parts out of 300 parts is combinations of 4 out of 300. Does everybody see my writing, like the last row? Yeah, it's not too small. It's okay. So that's the total number of ways. I can select 4 parts from these 300 parts. And now what I'm interested in is I want all of them to be from supplier A. So that means 4 from 100. And that's it. Or we can use the equation and we get the same answer. Any questions? Yep.
If there was a third supplier, could we just add another, right?
Yeah, that's a very good question. Yeah, so that's not in the book as much as I remember, but you are absolutely right. So, this distribution, there's only 2 classes, right? So we either have success or failure. So we have 2 classes, but you are right. If we had 3 suppliers, another supplier C, we just multiply that guy also, right? So we write. It's a very good question. So we write here number of ways from supplier 1, so NA from NA. So NA is the total number of parts from supplier A and small NA is the like let's say, like this is, for example, like 200 parts from supplier A, and we want to have, for example, 3 from supplier A, right? And this can go on as many suppliers as we have, right? NB from NB and so forth, right? And here we are going to have NA plus NB plus NC plus whatever we have, and here NA plus NB plus NC plus da da da. So it goes to as many as you want, but it's not in the book as far as I remember. Any questions? So let me explain the question, because I think it's a very good question, and even though it's not in the book, the probability is not in the book, we know all the tools to calculate it, right? So assume that, like this is another question, we have 100 parts from supplier A, we have 200 from supplier B, and we have, let's say, 300 from supplier C, right? So these are all in a bowl, right? And let's say we select, let's say, 10 parts, right? And from these 10, we want, let's say, 2 of them from supplier A. We want 3 of them to be from supplier B. And we want 5 of them to be from supplier C. Right? What's the probability of this happening? So again, we use, this is not in the book, but in fact, this can be in the exam, because we use the basically material from chapter 2 now, right? So based on material from chapter 2, we say, what's the total number of ways this can happen? Basically, I have to choose 2 from A, 3 from B, and 5 from C. So 2 from A, 3 from B, and 5 from C. And then here, what's the total number of ways? The total number of ways is choosing 10 from 600. And that's the probability. It's a very simple probability distribution, in my opinion. Any questions? Okay. All right. So the mean is NP for this distribution, where we define P as K divided by N, right? And this is very intuitive. The reason for this is that I have an urn that has, for example, 100 parts from supplier A and 200 parts from supplier B, right? Yeah.
Can you go back one slide, please?
Yeah, let's finish this and then I'll go back. Yeah. So I'm selecting 5 objects, right? So, and I define X as the number of objects from supplier A, right? So I'm choosing 5 objects from this bowl, and I define X as the number of objects from supplier A. So X can be 0, it can be 1, all the way to 5, right? So X is a random variable because it takes random values. So without using the equation, can you guess what's the expected value of X? Like in average, what value do we expect X to be, right? If we repeat this experiment many times and average the result, what is X? I'm not sure actually, let's do the math. So the average is going to be 5 times, because if we select more parts, there's basically x also increases, right? So if we select one part from this urn, right? If we select one part from this bowl, what's the expected value of x in that case? It's 1 divided by 3, right? Because that's the chance of, getting one piece from A, right? If we select 5 pieces, it's going to be 5 times 1 divided by 3, right? And that's this equation, that's NP. So again, I repeat. So in this bowl, I have 100 from supplier A and 200 from supplier B, right? Instead of choosing 5 objects, I assume I'm choosing 1 object, right? If I assume 1 object from this bowl, in average, how many objects do I have from A? 1/3, right? Because there's 1/3 A and 2/3 B, right? And this 1/3 here is this guy, P, which is K divided by N. So this P is chance of success in 1, if we choose 1 basically piece, right? And since you're choosing N pieces, you say NP. Yeah, what's the question, Taji?
Can you go back one slide, please?
This one?
Yeah.
Yeah.
Thank you.
Yeah, okay. Other questions? Okay. So let's look at another example. We have a list of customer accounts at a company that has 1,000 names, right? Of those 1,000 names, 700 have purchased at least one product. So we have 700 who have purchased the product. We denote that as P. And we have 300 who haven't purchased the product, right? And we are selecting 50 accounts, right? What is the probability that more than 45 have purchased a product, right? So we say, okay, more than 45, so it's going to be 46 from 700 times the remaining 4 from the remaining 300 plus, so this divided by 50 from, so we are selecting 50 total from 1,000, right? And then plus, so the next one is going to be quite similar. This one is going to be 47 out of 700 times 3 out of 300. And this is the same thing here, right? The total number of ways doesn't change, right? It's always the same number. Plus, plus, and the last term is going to be 50, all 50 of them are from 700, divided by 50 over 1,000. That's the answer, right? So there is, basically there are multiple terms. Any questions? So the next distribution is very, very important. But you don't really need that much practice for this one, because you should know that the distribution is Poisson, right? Usually, the most interesting part of any problem is to find out which distribution it is. Once you find out the distribution, you know, you Google the equation or you look at the crib sheet, right? For the case of Poisson, it's, I will tell you what's the intuition behind it, but for the case of this course, the question always has to tell you it's a Poisson distribution, right? So basically, we have a random variable x that is equal to number of events in a Poisson process, right? And the probability of x is basically this function, e to the minus lambda times lambda to the power x divided by x factorial, and x can be 0, 1, 2, 3, all the way to infinity, right? So where does, I mean, what processes are Poisson? Many processes that deal with counting. For example, the number of customers that enter Tim Hortons in a certain amount of time, right? Or you're manufacturing something, the number of, you know, cracks in that product per unit length, or the number of potholes. Or a very famous example is the number of radioactive particles that pass through any surface, you know, in 1 second. That number is also a random process, and that number is a Poisson distribution, right? And there is a very nice and easy proof that I will share with you, right? So one of the examples in the book tries to prove this distribution, but it's not really a good example, right? I will post something on Moodle. But basically, the idea for a Poisson distribution is if we look at, for example, the number of radioactive particles that pass through a unit surface in, you know, let's say 1 second, right? What we do is that we say, okay, this is 1 second, 0, 1 second. We divide 1 second into many smaller intervals, right? And we say in each one of these intervals, we can either have a particle, we define that as a success, or no particle passing through, we define that as a failure, right? And then the probability of, you know, success in all of these is quite small because these are very small time intervals, right? But there is so many of them, right? And then use the binomial distribution. This is a binomial distribution. Use the binomial distribution and you calculate the limit of the binomial distribution when this time interval goes to 0, right? So these basically, these intervals become small and small, and you calculate the limit of binomial as this delta t goes to 0, and that becomes Poisson, right? So there's actually a reason this Poisson distribution happens in real life, right? And this is the reason, right? So what is lambda? Lambda is the mean, right? Lambda is the expected value. So that means that, for example, in 1 second, how many particles do you expect to pass through this unit circle? Or in 1 minute, how many customers do you expect to arrive in Tim Hortons, right? And basically, this derivation from the binomial to Poisson was done by Simon Poisson very long time ago, 200 years ago, right? So very smart guy that thought about this 200 years ago. All right, so let's look at an example. So we have a copper wire, and the number of flaws follows a Poisson distribution with a mean of 2.3 flaws per millimeter, right? So if we look at 1 millimeter of this copper wire, we expect there to be 2.3 flaws. Find the probability that we have 2 flaws in 1 millimeter, right? So all we do is that we plug into the equation, right? So we had f of x for Poisson was e to the minus lambda times lambda to the power x divided by x factorial, right? So we have lambda, mu and lambda are called the same thing, right? So by the way, for Poisson distribution, the mean is denoted as lambda, but it's the same as mu, right? So for lambda, we plug in 2.3, and for x, this is x, and this is lambda. So that's it. So the probability that we get is 0.2, 0.26, right? So question, what is probability of x equal to, let's say 5? How many of you think the probability is more than this number, and how many of you think the probability is less than this number? So do you think the probability is more than this number? Raise your hand if you think so. And do you think the probability is less than this number? Yeah, there you go. So it is less than this number because the average number of flaws was 2.3, right? So having 5 flaws, we can actually calculate it, right? So for having 5 flaws, it's going to be, I'm actually curious because I will show you the distribution of the Poisson. The mean is not necessarily the highest number, right? That's the tricky part. But let's calculate it, right? But I think that for 5, the probability is less than this number. So e to the minus 2.3 times 2.3 to the power 5 divided by 5 factorial, right? Can somebody calculate this, please?
0.053.
Thank you. 0.053? Yeah, so it's much smaller, right? So let me show you, it's a little bit later, but let me show you the basically curve for the Poisson distribution. That's how it looks like, right? So this is for lambda equal to 1, the yellow curve. The purple one is for 4. And we see that, around 4, we have the highest probability, right? And this one is for lambda equal to 10. And here, again, that's not always the case, right? But for this distribution, we see that, for example, around 10, the mean and where we expect the highest probability is at the same location. Right? Okay, let's go back. Okay. So this example was a relatively simple one because the question gave us how many flaws we have per millimeter, and at the end it asked us what's the probability of having 2 flaws in 1 millimeter, right? So let's make it a little bit more complicated. So we want to find the probability of 10 flaws, but instead of 1 millimeter, the question is asking us that the length is 5 millimeter now, right? So it's not 1 millimeter as before. Before was per millimeter, here is in 5 millimeter, right? So the first thing we have to do is in the Poisson distribution, right? Here lambda is the average number, right? So again, here what we should do is, where is it? So we have to find out what is lambda for the new number, right? So lambda is going to be 2.3 flaws per millimeter, but this time we have 5 millimeter length. So our length is bigger, right? So this basically means that in average, we expect 11.5 flaws in 5 millimeters, right? And again, now that we get this number, we plug in, so we plug in x equal to 10. But the only difference with previous example is that it's a different lambda. It's not the same lambda, right? So in my opinion, this is also really easy. All you need to do is to calculate the expected value for whatever length the question is interested in, right? Any questions? Okay. So the next question is calculate the probability of at least one flaw in 2 millimeters, right? So X denotes the number of flaws in 2 millimeters of wire, and I have to calculate probability of X equal to 1. So this is going to be probability of X equal to 1 plus X equal to 2. This is an infinite sum, right? Because I might have 1,000 flaws. Right. So now we are quite good at that, right? Once we have, like so many sums, we look at the complement also, right? And in this case, the complement is easier to calculate, right? So what I do is that instead of doing that infinite sum, I calculate the probability of 1 minus probability of having no flaw. Right? And another thing that I have to do here is that the previous question told me that in 1 millimeter, I have 2.3 flaws. So in 2 millimeters, in average, I have 4.6 flaws. Right? So my lambda is going to be 4.6. Any questions? Okay. So the next question, the average number of radioactive particles passing through a counter is in 1 second is 4. So in 1 second of time, in average, we see 4 particles passing through. The number of particles follows Poisson distribution. What's the probability that 6 particles enter in 1.8 seconds, right? So the first thing we have to do is I have to say, okay, now my time interval is 1.8 seconds. So my new lambda is going to be 4 times 1.8, right? So that's my new lambda, and this is my X. And that's it. The rest is just plugging into the equation. Any questions? Okay. So that's the probability. Any questions? Okay. So these are the curves for Poisson distribution for different. Poisson has only one parameter, and that's lambda, right? In the next chapters, we'll see other distributions that have more than one parameter, right? And what's interesting is that when lambda is large, for example, 10, the shape of this thing becomes like a bell, right? For 20 is also the same shape, right? So for 20, it's going to be something like this, right? And this is a famous distribution. Does anybody know? We haven't covered it yet. Does anybody know what's the name of this distribution? The bell-shaped distribution? Yeah. Exactly. This is the normal distribution, right? So we'll see this normal distribution a lot in this course, in the following chapters, right? So Poisson distribution for large lambda is actually a normal distribution. It's quite close. Okay. So we covered a lot of, material in these 2 chapters, and I want to talk very briefly about one application of these, the material that you learned in chapters 2 and 3. How many of you have seen this movie, Moneyball? So it's a good movie. Netflix has it. I really enjoyed watching it. And basically the idea, I try not to spoil the movie, But the idea is that this coach tries to use basically statistics for managing a team, right? He becomes a general manager of a team that has very limited money, right? And instead of, relying on gut instincts, he tries to use stats to purchase players, right? I won't spoil the movie. I won't tell you what happens, but it's an interesting story about what happens, right? And there are many stories like this, in real life. You hear about, startups that look at one problem and they try to basically, the way that that problem was done was sort of arbitrary. Managers just decided, based on their gut feelings to do things, and they formalize that process, right? One example that is, relatively close for you guys is that there's a startup. It's called Sport Logic. How many of you have heard about Sport Logic? So not many. So actually nobody. So Sport Logic was a company that the founder was a PhD student at McGill, right? It's a new company. And basically what he did is that he looked at hockey games, right? And instead of, again, quite similar to this movie, right? Instead of, again, managers relying on their gut feelings to buy players, right? He basically analyzed the videos and basically brought statistics into how much every player is basically worth, right? And the last I heard about Sport Logic was like 2 years ago or a year ago, and more than half of NHL teams have contract with the company, right? They pay them a lot of money to basically manage the team for them. And now they have expanded to other sports also, in addition to hockey, right? So, your life is, in my opinion, an optimization problem. You have limited resources, right? And if you can somehow, if you see any problem in your life that you can somehow, formulate the problem into a math and stats problem, then, you have a very good idea in front of you. So basically, the take-home message is that I agree with you. The material in these 2 chapters can be very, very dry and abstract, but the only solution for that is you have to solve many sample questions. And, you get a feeling that, these are actually quite similar to real-life scenarios. So that's it for what we cover in the midterm, but I do want to talk about the next chapter because some material in the next chapter is quite similar to basically to chapter 2, right? You'll see that chapter 4 is quite similar, to chapter 3. The only difference is that instead of a discrete random variable, here we have continuous random variables, right? So, and because of that, I think it opens your perspective, and it can, in my opinion, help you in your midterm exam. So there are a few mistakes. These are in the previous edition of the book. I'm not sure if they have been fixed in the latest edition. I haven't seen the latest edition. But if you have the previous edition, you can correct these. So here, as I mentioned before, we have PDF, right? So in the previous chapter, we called PMF, probability mass function. And here we call these probability distribution function, right? And the only difference is that our x here is a continuous random variable. That's the only difference. There's no other difference with the previous chapter. X is, something that takes continuous values, right? So again, we have some restrictions over f of x. For example, f of x is always positive. The integral of f of x is 1. That means that all probabilities add up to 1. Probability of x being between a and b is equal to integral of f of x from a to b, right? You remember for the previous chapter, it was sigma, right? And finally, f of x equal to 0. It means that there's no area exactly at x. So one notable difference, which is also quite confusing for many of you, is that, do you see actually any difference with PMF? Do you remember the properties of PMF? One of them is missing here. So before I say what's missing, let's look at an example, right? And hopefully you remember what's missing. So X denotes current in a wire in milliamps, right? Assume that the range of X is between 4.9 and 5. And for that range, I have a constant probability, right? So meaning that the probability, basically the current can take any value between 4.9 and 5 with equal probabilities. Okay, like this. Yes. So there's equal chance of the current being anything between 4.9 and 5. What's the probability that the current is less than 4.95? So 4.95 is here. Right? So the probability is going to be the integral from 4.9 to 4.95. And it's a constant function. The integral is x. And the probability is 0.5. And when we look at the curve, it does make sense because 4.95 is right in the middle. So this area is half. Right? So do you see anything about this PDF that is a little bit strange? So this PDF is for continuous random variables. Is there anything that this PDF has that PMFs in the previous chapter couldn't have? Yeah?
Can you bigger than one?
Yeah, yeah. What was your name?
Roger.
Roger, yeah. So that's a very good answer, right? So this f of x is more than 1, right? And it can be very counterintuitive, right? So we know that probabilities can't be more than 1. How come this is a valid PDF? How come this is 10? Any ideas? So the reason that PDF can be more than 1, it can be 100, it can be 1,000, right? It can be anything. It can't be negative, right? So for PMF, we restricted PMF to be less than 1, right? PMFs are always less than 1, right? Because, for example, probability of X being 4 can't be like 1.5 or can't be 10. But for PDF, we don't have this restriction, right? It can be more than 1, right? And the reason is that PDF is not probability. It's probability density function, right? And what is probability is the integral of PDF, right? PDF itself is not probability. It's the integral of PDF that is probability, right? So, for example, here, the integral is this area under the curve, right? As long as the area under the curve is less than 1, it's okay, right? So you can have a function that's more than 1, but the area under the curve is less than 1, right? In calculus, we know that can happen, right? And we see one example here. The function itself is more than 1, but the area under the curve is always less than 1 or equal to 1 if we calculate all of the area, right? So remember, PDF is not probability. It's the integral of the PDF that's probability. Okay. And again, like previous chapter, we have the concept of CDF, right? Again, in the previous chapter, cumulative mass function was the sum. Here, cumulative distribution function is the integral from -infinity to x, right? And that's called f of x. So let's look at our example, right? So f of x is 10 between 4.9 and 5. We want to find out capital F of x, right? And that's the integral of this function, right? So for less than 0 is 0, because the integral of 0 is 0, so it's 0. And remember, f of x is 10. So f of x, if x is between, I think I have the, no, I don't have the calculation. So if x is between 4.9 and 5, f of x is going to be integral from 4.9 to x. F of x is 10 d of x, right? And if you do the integral, you get this function here, 10x minus 49. Right? And after 5, you don't even need to do the integral, because we know that here there's no mass, and we know that the probability must reach 1. So after 5, probably f of x is 1. Right? And this line is this line here. So this is f of x, capital F of x, and this is small f of x. Any questions? Yeah?
You have the less than or equal to sign for x is less than or equal to 5, but then you also have 5 is less than or equal to x.
Yeah.
Could you have x is equal to 5 in one of the brackets and x is equal to 5 in the same different bracket as well?
Yeah, that's a very good point. What was your name again?
Mikey.
Mikey. So Mikey, you always find mistakes in the slides and in my calculations. This one is not a real mistake, right? So you're right. When we define a function, we can't define it for, we can't define, a function means that if I give you x equal to 5, you should give me one answer, right? You can't give me multiple answers, right? So how come x equal to 5 is both here and here? For probabilities, it doesn't, for continuous probabilities, it doesn't matter because they are equal, right? So yeah, this is not a mistake, but you're right. One of them, we have to be careful that function can't take two values at one point. Yeah.
Okay, thank you.
Other questions? Okay. So if there's no questions, I stop here. I will be around for like 20 minutes if you have any questions about anything in chapter 2 or 3.